This is lecture 4. So in the previous lecture where we stopped, we started looking into systems, whose transfer function whose impulse response changes with time, right? And more particularly, we were looking into something called a linear periodically time varying system. Without getting into the nitty-gritties of it, it's essentially a system the characteristic of it changes with time periodically, right? For example, the case that we saw was, let's say there is a system where the system itself changes with time. That is, I have some signal, or rather I have some time varying signal, not the input signal, some time varying signal that is multiplying the input. This is just an example. Let's say your input is e to the power j omega naught t, and it is, when it goes inside the system, it gets multiplied with some other complex exponential. Let me call it omega st. So the output is naturally e to the power j omega naught t times e to the power j omega st, which is e to the power j omega naught plus omega st, right? So clearly we see that this is something weird is happening, which never happens in a LTI system. What weird thing is happening? The weird thing that is happening is your input is at a frequency omega naught, but your output is at a frequency omega naught plus omega s, right? So there is
clearly a frequency shift that has happened, and this cannot happen in a linear time invariant system, right? So this is linear because if I multiply the input sum by some factor alpha, the output is also getting multiplied by some factor alpha. Note that alpha is independent of time, so that's it's a kind of a scalar. So that's an important caveat to mention. So the linearity part at least is getting satisfied. Similarly, if we apply another input beta e to the power j, let's say omega 1t, so the output will be beta e to the power j omega 1 plus omega st, right? And now if you apply simultaneously both of them together, that is, you apply both of them together, what's going to happen? Again, the same thing is going to happen, that the output will be the summation of these two. So hence linearity is satisfied, but time invariance is not satisfied, right? So linearity is satisfied, linear but not time invariant. This is something that we saw in the previous lecture also. But the key takeaway from the previous lecture that we are bringing into this lecture is the fact that the output can have a frequency shift, right, which cannot be the case in a LTI system, right? Okay, so now one of the most frequently used case studies or examples or applications that you will have in this course is a system like this. It's generally called a mixer, or it's called a mixing operation, because you're kind of mixing two signals, you're multiplying two signals. But even before getting into that, there are some analysis techniques that will be useful for us going forward, and that is what I'm going to spend next few minutes on, right? For example, a very common occurrence that will happen in this course later on will be a situation like this. So let's say I have a mixer, or I have a multiplier, where one of the inputs is not e to the power j omega t, but let's say it is a square wave. Like before, we call it s of t, right? Your input is, let's say, e to the power j omega naught t. So what is the output? Output is naturally st times e to the power j omega naught t. So now the question that will come regularly is, what is the frequency component of the output, right? So let me redraw this. So the question that will regularly arise is the following.
So I understand the output is st times e to the power j omega naught t, where st is the square wave. The question that will arise is what is the frequency component of output, right? So, or rather, what frequency components are present at the output? And we'll do the analysis now, but the reason we are doing the analysis now is for you to appreciate the fact that from next time onwards we'll reuse these results directly without doing the analysis in a full-blown manner, right? So we'll do it now once and then start reusing them later on. Okay, so let's do it. So how do I go about analyzing this? If you recall, your s of t is nothing but a periodic signal, right? And it can be broken down into sum of complex exponentials weighted by some scalar quantity, and the value of those we can get from the Fourier series analysis, right? And when we did that, what did we find? We basically found that s of t can be thought of as summation of, if I assume that this is Ts, right? Periodicity is Ts, and if I define, let's say, omega s to be equal to 2 pi over Ts, then I can say your s of t is nothing but summation of some sinusoids. There will be a DC term, there will be some DC term, then there is an exponential term, right? Then there will be another term e to the power j 2 omega st, then there will be another term e to the power j 3 omega st, and so on. Similarly, we will have terms for negative omega s also. So you are going to have minus j, negative omega st, and so on. And this essentially is the Fourier series expansion, right? But the coefficients which are in the brackets can be exactly evaluated, right? We have done that before, so I will just pull the results. So the DC term, which is independent of omega s, is essentially the power, right? It's the average value of the system in this case. So which is essentially half, right? If I assume this goes from sinusoid, this s of t goes from 0 to 1. Let me also write it down, right? Similarly, we saw that the coefficient of this term, the second term, that is per j omega st, is essentially 1 over pi, right? Or let me simply okay, let's leave it like that. Similarly, we saw that the coefficient of the even harmonic terms are essentially 0, right? And similarly, you are going to see the third harmonic term, or the coefficient of e to the power j3 omega st will be 1 by 3 pi, and so on. And similarly, you are going to have something on the left hand side also. I'll just call it a negative 1. You're going to have a phase term. Let's ignore that for the time being. So actually, I kind of jumped the gun here. I did not say that whether this s of t is centered around 0, that is, if the s of t is, if the 0 of the s of t is here, or it is slightly shifted, right? So what will happen if it's slightly shifted? If it's slightly shifted, there will be an additional phase term, right? So which I have not really taken into account. So what I will do is what I will essentially do is to simply take the amplitude. But if I take the amplitude, I cannot magnitude. If I take the magnitude, I cannot write it in this form. So I'll just keep it as A0, A1, A2, A3. And I will simply say that mod of A0, or in this case A0 is equal to half. There is no doubt about that. But mod of A1 will be 1 over pi. Similarly, mod of A3 will be 1 over 3 pi. A2 will be 0. Similarly, mod of A negative 1 will be 1 over pi, and so on, right? So if this is the case, then what is the final output, right? Note that it's not like we do not want to take the information of the phase, but
but we are only interested right now in the strength of the signal. And if to get a gauge, to gauge the strength of the signal, it is sufficient to know the magnitude part of the coefficients of each of the Fourier terms, right? So what is this? So now what is the final output? Final output is nothing but s of t multiplied by this. So essentially all of these terms get multiplied by e to the power j omega naught t. So your v naught t will be nothing but, we'll have a term of a naught times e to the power j omega naught t plus a1 to the power j omega naught plus omega st. Similarly, you are going to have a negative 1 e to the power minus or e to the power j omega naught minus omega st plus so on, and a2 will go to 0. You are going to have a3 e to the power j omega naught plus 3 omega st, a negative 3 e to the power j omega naught minus 3 omega st, plus so on and so forth, right? So this is what we are going to have. What is the takeaway? The takeaway is, if you multiply a monotone signal which has only single frequency component at plus omega naught, and you multiply it with s of t, which is a periodic signal, right? In this case, a square wave, 50% duty cycle square wave. So in that case, what we are going to see? We are going to see a whole bunch of tones, and the tones spacing will be, you are going to see tones at, firstly let me write down the spectrum of s of t, that is s of omega with respect to omega. You are going to have a tone at 0, you are going to have a tone at omega s, you are going to have a tone at 3 omega s, then 5 omega s, and so on. Similarly, you are going to have a tone at negative omega s, negative 3 omega s, and so on. And your input, let's say it is at omega naught. I can choose any point in this line as omega naught. Let's say I choose this one to be omega naught, right? So what will be, also mark the strength of the tones. Maybe I will mark it slightly higher amplitudes. And so on. So if this is the case, what's going to happen? You're going to see an output mod v naught j omega. You're going to see an output such that this tone, so let's go back to the previous page. So what are you seeing? You are seeing that this tone is getting multiplied with a naught and creating a tone at omega naught, right? So that we are anyway seeing. So that we are going to see one tone at omega naught, and the strength of the tone will be multiplied by the strength by a naught. So what is a naught, or the mod of a naught? So this is the mod of a naught, right? Similarly, this is mod of a1. Similarly, this is mod of a3, right? So you are going to have one component with at omega naught, but it is going to get multiplied by mod of omega naught, mod of a naught. What is the second? What is the other component you are going to get? You are going to get a component at omega naught plus omega s, right? So essentially, this tone of omega naught got right shifted by omega s, right? So this is omega naught. So on this side, if I go by omega s, we're going to have another tone, and the strength of that tone, if the original tone had a strength of unity, this gets multiplied by mod of a1, right? So what else? Note that you have another strength at omega naught minus omega s, right? So So this omega naught not only shifts to the right, it also shifts to the left, right? So it also shifts to the left, and again it shifts to the left by the same same omega s. So you get here the strength of this tone is mod of a minus 1, right? And similarly, you are going to have another strength at 3 omega s, right? So this is this will be omega naught plus 3 omega s. Similarly, you are going to have a tone at negative 3 omega s plus omega naught is here. Right? So from the next time, what we'll do, we'll not do all this analysis full blown. We'll simply assume that we are comfortable with the fact that if you have a square wave, it's going to have a tones at omega at harmonics of omega s, and this if your signal is also a sinusoid, or in this case a complex exponential, it is going to get shifted by uh, uh, in the frequency axis, it is going to get shifted by the locations of the tones of S of t, right? So now note that e to the power j omega naught t is not a real signal, right? What is a real signal? Cosine omega naught t is a real signal, right? So, but cosine omega naught t can also be thought of as half of e power j omega naught t plus e to the power minus j omega naught t, right? So now note that this is a linear system, so I can still use superposition. So I can say that I know the response to this, or rather let's get rid of the half term. I'll just say that your input is twice cosine omega naught t, just to keep the algebra simple, or rather keep track of all the terms without making an error. So we know that e power j omega naught t, I mean the spectrum right on top is the spectrum here is essentially how what will be the output if the input is e power j omega naught t. Now the question is, what will be the output if the input is e power negative j omega naught t? So we essentially do the same analysis, and now we apply a tone at e power minus j omega naught, right? So here this is negative omega naught, and what will happen to this tone? Exactly the same analysis with respect to the previous tone. So this negative omega naught tone is going to go right to a position of minus omega naught plus omega s. So essentially omega s minus omega naught, right? So I did not write it here. So this is omega naught minus omega s. So now you are going to have a tone at use a different color. I should have used blue here, so I'll use blue here. So I'll use the magenta here. So you're going to have a tone at minus omega naught plus omega s, that you're going to have a tone somewhere over here, right? So this is at minus omega naught plus omega s. Similarly, you are going to have a tone at minus omega naught plus 3 omega s, right? So around 3 omega s, omega naught to the right and omega naught to the left, we are going to have 3 omega s minus omega naught. Similarly, you are going to have a tone clearly, I mean the negative omega naught tone will get multiplied with the DC, right? And you are going to have a tone at minus omega naught also, right? So you're going to have a tone at negative omega naught also. It's kind of getting messy. So this is minus omega naught. Just put it here, minus omega naught. Similarly, you are going to have a tone at minus 3 omega s minus omega naught, that is here, right? So when you apply a real signal, right, a cosinusoid for example, you are going to have two tones around the tone of s of t, right? So again, just to quickly recap, so your tones of s of t were centered around omega s, 3 omega s, negative omega s, negative 3 omega s. So after getting multiplied, the tone shifted to omega s plus omega naught and omega s minus omega naught. Similarly, 3 omega s plus omega naught and 3 omega s minus omega naught, right? And you have a tone at 0 for s of t. So 0 plus omega naught and 0 minus omega naught, that is also visible. So what will be the final output? Final output essentially will be summation of all the tones, and whatever you get is the final output, right? This analysis is crucial because you will see that going forward, it is very important for us to visualize what happens to an input if it gets multiplied with periodic signals, and if the periodic signal does not necessarily have a single tone, right? So an extension of this is what I took an example that input is e power j omega naught t. If the input is not e power j omega naught t, and input has a spectrum, right? So if the input is a generic x of t, and you multiplied it with e to the power j omega naught a, or e to the power j omega s t, right? So what will be the output? The output in time domain is simple. It's xt multiplied by e to the power j omega st, right? But what will be the spectrum? For this, obviously, you will need to know what is the spectrum of x of t. If let's say I know that the spectrum of x of t is it's not a periodic signal. Let's say it's an aperiodic signal, right? So let's say the spectrum of x of t is something like this. Instead of a tone, it has a spread around some omega naught. And naturally, if it's a real signal, you are going to have a same thing on the negative axis. The phase component can be either the phase around omega naught and phase around minus omega naught can be the same or negative of each other. But I mean that's regardless. Let's concentrate on the magnitude for the time being. So if this is the spectrum of x of t, that is x of j omega, and you multiply with e power j omega st, where let's say e power j omega st, the tone of e power j omega st is here. Similarly, you are going to have something at negative omega s. What's going to happen if I, using the same principle? So all of you must have done convolution in, I mean, what happens to convolution? What happens to the Fourier transform if you do multiplication of two signals in Fourier domain? It essentially gets convoluted, right? Convolved rather, right? So in frequency domain, what is essentially happening is, just like here, the tone at omega naught got shifted to omega naught plus omega s, right? Similarly here, so whatever spectrum you see at omega naught will get shifted to omega s plus and omega s minus, right? So essentially, so this guy is going to get multiplied with this guy, or rather, it essentially gets multiplied, but after multiplication in time domain, it's going to shift. This will shift to omega s plus omega naught, right? So this is going to shift here, and this is going to interact with this, and it is going to shift at omega s. It's basically the negative omega naught will get shifted to the right by a value of omega s. So this will get shifted here. So you're going to get a tone. You're going to get a tone at here. So this is omega s plus omega naught, and this is omega s minus omega naught, right? Similarly, you are going to have a tone on the left hand side also around omega s, if this is omega s, negative omega s. So you're going to have a tone negative omega s plus omega naught and negative omega s minus omega naught, right? Okay. So, and like before, if instead of e power j omega st, if it were a square wave, then you are going to have, I made a mistake, so I should have said you have two tones. So that's why you got omega s and minus omega s. Instead of these two tones, if you had s of t, right? So then just like before, Just like before, you are going to have a whole bunch of these x of j omega spread around the entire frequency axis. I'm not drawing it, but I hope you can visualize it, right? So till now, we have kind of been doing some sort of very rudimentary signal processing, or I shouldn't say signal processing, it's more of rudimentary analysis of signals using Fourier transform, Fourier series, and so on. And it kind of has been a refresher of whatever you have learned in your undergrad program. Uh, so let me now not bore you anymore, and let me start giving you some idea about what a radio frequency signal chain looks like, right? And and kind of what is the reasoning behind it looking like it, right? So now, why do we at all need a radio frequency signal chain? It's because ultimately we want to transmit something and we want to receive something through a wireless channel, right? Note that it's a wireless channel, it's not a wired channel. So now one key thing about wireless channel is that it is shared with everybody, right? So it's not, I cannot really claim that this part of the wire is mine, this part of the air is mine, and that part of the air is yours. Cannot do that, which means that if I transmit something over the air, so it belongs to everybody. So now in the first lecture example that I talked about, obviously if everybody is talking in unison, there is no way you are going to figure out who is talking, right? So something has to be done in order to ensure that whoever wants to use a wireless channel has a dedicated part, something dedicated to that person or to that individual or to that device, so that when another device or another person is ready to talk or transmit anything, it does not get they do not come in each other's space, right? A technical term is they do not interfere with each other. Okay, so now so how can we really do that? So now if you think about it, if I want to transmit the voice that I am right now speaking with, so what should I do? Firstly, this is an acoustic signal, so I need to have some sort of sensor which converts that acoustic wave into electrical waves, right? Into currents and voltages. So we'll not get into how that is done. We'll start off with the assumption that the currents and voltages of my voice are available, right? So we'll assume that. So firstly, assume that the signal that we want to transmit are available in the forms of, in terms of analog voltage and currents, right? You will understand the need why I say analog later on in the course, but for the time being we'll limit ourselves. It has to be in the form of analog voltage and or currents, right? It need not be both, because if I have voltage I can derive the current out of it regardless, right? So this is an assumption, so which means that I have this continuous time nice looking waveforms available to me and I want to transmit, right? So another terminology is, so typically these signals are of low frequencies. I'll say within quotes low, because what is low and what is high is relative. Low frequencies. And if I say it ranges from kilohertz to few megahertz, right? Maybe tens of megahertz, right? So typically these signals are of low frequencies, and I can simply say also centered around omega equal to 0. Okay, so it's not a it's not a signal like this. Generally the signals are not like this.
Generally, the signals are not like this. These signals, the voice signal or the or even any audio or video signal that we tend to transmit, they have a they are centered around DC. Okay, and when I say this, this can be of the order of kilohertz to the span can be of the order of kilohertz to megahertz. If it's an audio signal, it's few kilohertz. If it's a video signal, it's few megahertz. Now, with the recent trends of augmented reality and virtual reality and all, uh, the requirements have substantially increased, and people are going for much higher bandwidths. But the concepts still remain the same. Okay, okay. So these signals are typically, again, the terminology that is used are called, these are called baseband signals, right? So these are called, we'll call them baseband signals. Okay, or in abbreviated form BB. Okay, so now these baseband signals, which are these signals that we want to transmit, which has all the information, right? So again, this VBB has all the information that we want to transmit and receive. Okay, so now, given that these voltage waveforms at some kilohertz to megahertz range are available to us, and I want to transmit them over a wireless channel, what are the options available to me? Given that there are like millions of devices, millions of people using those devices who want to transmit and receive these signals simultaneously. So naturally, I cannot really transmit them just as is, because all of them will interfere with each other, right? And nobody will be able to make out what we are transmitting, right? So transmitting cannot be done just like it. So what are the ways of what is the most obvious way of to ensure, or what is the most obvious way of ensuring that we transmit these signals without any problem, right? So now, what is the major problem? The major problem is, let's say I have an user 1 and I have a cell phone, and my cell phone is trying to transmit something between 0 to some frequency FBB. Okay, I have a user 2 which is also trying to transmit something maybe from 0 to twice FBB. Another guy is trying to transmit something from within FBB by 2, and all of them want to transmit, and there is probably one receiver here, so they want to transmit. There are receivers who are also willing to listen, right? So now, since this is in a wireless channel, this is wireless, so this signal goes there, this signal goes here, this signal goes there. Similarly, this signal goes there, this signal goes there, this signal goes there, and so on, right? So everybody gets everything. They are transmitting at the same time, same frequency. You do not know what frequency who is receiving what, right? I mean, we receive everything, but you won't be able to make out anything, any heads and tails about it, right? So now, and given that you cannot really say that now you transmit and now you talk, now you cannot. So what is the only other option to do? You have to ensure that all these users do not transmit at the same frequency, right? The solution is don't transmit at the same frequency. Okay. So now how do you ensure that people don't transmit at the same frequency, because all of our voices are of similar frequency range. So because you cannot really ask me to change my tone, what I can do is take the input, right? Take that input inside the device, because a device is my property. I am not really transmitting the device in a wireless channel. If it is within the device, I can do something to move this signal, which is centered around 0 to FBB, to some other frequency, and then translate it, then transmit it, right? So the solution is, then the natural solution is shift the baseband signal to a different frequency for each user, right? So now, given that we have seen, right, how to move frequencies from one frequency, from one point to another in the frequency spectrum, how can we do that? Easy peasy. We basically need to multiply with the complex exponentials, right? Our complex exponentials are not available, but we can always multiply with the sinusoid. So now what are you doing? We have an user 1 who is trying to transmit frequency FBB, and you have a user 2 who is also trying to transmit within the same, basically the same baseband signal, right? Having different content, obviously, but frequency is more or less same. We want to transmit this. So what do we need to do? We need to basically multiply with a sinusoid. I'll call it sine. Let me use another term here. I'll call it sine omega LO, sine, or we call it sine omega LO 1 times t, and I multiply this guy with another frequency. I call it sine omega LO 2 times t. So what's going to happen? So the output will be, in time domain, it will be multiplication of this baseband signal 1 times sine omega LO 1, and this baseband signal, so this is in frequency domain, so I should not write t. So in time domain, this will be VBB 1t times sine omega LO 1t, and this is VBB 2t times sine or cosine. If I restrict myself to the magnitude, then it really doesn't matter. So what's going to happen if omega LO1 and omega LO2 are not are kind of separated? So then, so in frequency domain, what's going to happen? So let's say this is omega LO1 and this is omega LO2. So I'll have the user 1 will take up spectrum around omega LO1, and user 2 is going to take up spectrum around omega LO2, and this will be FBB on this side, this will be FBB on other side, this will be FBB on this side, this will be FBB on the other side. And now if both these are connected, let's say I add them up and send it to an antenna. This is an antenna. So in the wireless channel, what are you going to see? In the wireless channel, we are going to see a spectrum around omega LO1 and a spectrum around omega LO2. Similarly, on the negative axis, we are also going to see. So here also, you are going to have a negative
frequency component, because real signals kind of are symmetric or anti-symmetric around DC, right? And now you can transmit this, because now the spectrum on around omega L1 and the spectrum around omega L2 are not overlapping on top of each other. Now you can transmit this. Now, as long as the user at the receiving end knows that he or she is going to listen to omega L1, right, or omega L2, you are good, right? So there has to be a handshaking upfront between somebody who is transmitting. Let's say user A is transmitting to user B, then A and B should know a priori that okay, A is transmitting in around frequency omega L1, that is this channel is transmitting using this channel. I better listen to that channel. It's like a radio. You tune your knobs and you better listen to that channel omega L1, then I'll be able to listen to the user A. If I turn my knob to omega L2, I'll not be able to listen to user A. I'll probably be listening to another user, right? That's what exactly happens in a radio, right? When you turn your knobs, you are basically tuning into channels that you want, right? When you turn your knob, what you essentially do is you change these omega L1s or 2s or 3, right? So if you turn your knob and you go to 93.1 or whatever FM channels you are I do not know exactly the channel numbers, but yeah, so 90x point something and 90x point something else, 90y point something. So you keep on turning the knobs. You are essentially saying, send me I would like to listen to a signal around that particular frequency, and if somebody is transmitting, which is the station, the radio station that is transmitting around that channel, you are going to capture. In case of cell phones, that doesn't really happen, because obviously for security reasons there are a lot of digital security algorithm that runs to ensure that you do not listen to all channels. So that's why you are not able to. That's why you can only connect to one user at a time and not necessarily multiple users. Connecting to multiple users used to be a problem long back, but no, not as much nowadays, right? Okay, so we'll stop here for this lecture. In the next lecture, we are going to see, given that this information is available to us, what should a receiver architecture looks like, right? And then take it from there.